another free tutorial video. This time we're going to be addressing a question that came in the other day on a very specific part of the discounted cash flow analysis. And I'll paraphrase the question right here. How do you pick the terminal multiple to use in a DCF when you're calculating terminal value for use in the analysis? And just to show you exactly what we're talking about, I have up here relatively simple DCF analysis for a steel manufacturing company, Steel Dynamics. And typically you will project the company's free cash flow 5 to 10 years into the future. You'll get to some type of number at the bottom for unlevered or levered free cash flow in each year, depending on how you've set up the analysis. You will take the net present value of those free cash flows and then add it to the net present value of the terminal value. The terminal value just represents the value of the company out beyond year 5. So going into year 6, year 7, year 8, year 9, and so on and so forth, what is the company's value going out into all those years? And there are a couple of different ways to do it. You could assume a long-term growth rate and then match it up with a discount rate and calculate it based on that, and then take the net present value of it. Or you could apply a multiple, either to the company's final year free cash flow, or to their EBIT, or to their EBITDA, or really any other metric that you want. And then based on that, you can get to what's known as their terminal value, which represents, again, the value of the company after the period that is shown in your projection years. So here, we've chosen to use the terminal multiple method, and what we've done is take the company's EBITDA in year 5, and then apply a certain multiple to it, 5.9x here, and that gets us to our terminal value. So the question is, how do you pick this number? How do you pick this 5.9x? How do you know it's not 7x or 4x or 3x? What do you do, and how do you think about it? So if you look in a lot of interview guides and other resources, and even some textbooks, they'll say things like, you look at the multiples for the company set of comparable public companies. So you'll look at the public comps, and then you'll use something in that range. So with our example here, with Steel Dynamics, for example, we might find an equity research report or other industry sources on the company. And then we might find, if you scroll down here, other sets of comparable companies. So here we have other companies that produce iron ore, other companies that produce scrap, other companies that are in the steelmaking industries. And we could look at these and say, okay, well, the average enterprise value to EBITDA multiples are 6.6x and 7.7x, and then 6.2x and 8.4x. And then if you go down 5 to 6x multiples in that range, and if you keep going down, you'll see 6x to 7x, and then some of these multiples get a little bit higher. Some of them go above 8x, but it seems like for the majority of these companies, the multiples are all in that range of around 5, 6, or 7 times EBITDA. And some people will just stop here and say, okay, well, you just pick something in that range, and then that's it. That's what you use for your terminal multiple in a discounted cash flow analysis. Of course, as usual, the real answer is somewhat more complicated than this. And specifically, we think there are 3 main problems with using the method that I just showed you. First off, multiples like enterprise value to EBITDA and enterprise value to EBIT will often decline over time as a company's growth rate slows down, and as the industry as a whole, the growth rate there also slows down. So you'll see these stories in the news about 50x revenue multiples for startup companies, or paying 500 times revenue for some new hot tech startup. But you're not going to pay that type of multiple for a mature manufacturing company because the growth potential is much lower. It's already a developed industry. Its cash flows cannot possibly grow that much higher in the future to justify this type of multiple. Now, another problem with this method of just looking at the comparables is that the terminal multiple that you pick also has to imply a reasonable terminal growth rate. And the key point here is that a multiple by itself is not valuation. It's really just shorthand for valuation. And in this lesson, I'm going to show you how to actually calculate the terminal growth rate that is implied by a given multiple. Because if you know the company's free cash flow in their final year, and you know the discount rate you're using, you can actually calculate the long-term growth rate that the multiple you pick implies. And then you can take that and say, let's say we go with that range of 5x to 8x for the multiples. Does that actually make sense in terms of the growth rates? In other words, do we get growth rates that are the same as the US GDP growth rate or below that? Or do we get growth rates that are much higher than that? And those are the types of tests and the cross-checking that you often do and that you should do in this type of analysis. And then finally, the third flaw here is that when you're looking at a set of comparables, it's not really about picking a specific multiple from that set. It's always about the range of values. So if the median multiple for many of these sets appears to be 7.5 times EBITDA, that's great, but that's not going to be the sole number that you look at. You're always going to look at a range of values. In our analysis here, for example, we have terminal EBITDA multiples going from 4.5x to 8.5x. This range is probably too wide, to be honest. In most banking and other finance analysis, you won't see a range this wide. You might see more like 5 to 7x, so that might be a little more reasonable, but you're always going to see some type of range with this. You're never going to see just one number used, and that's a point that a lot of people miss here. The first and third points here are self-explanatory, but the second one deserves some additional explanation. How can you actually calculate the implied terminal growth rate from a multiple like this? Now in our Excel file here, I already have this formula entered. So for this 5.9x terminal EBITDA multiple, you can see the formula right here. I'm taking our baseline terminal value, I'm multiplying by the discount rate, and then I am subtracting cell M59. Now if you go down, M59 is just the final year unlevered free cash flow for this company. So that's in the numerator, and then the denominator is just that same final year unlevered free cash flow plus the terminal value. Needless to say, this is not exactly an intuitive formula, and if you just look at this, it's really hard to see this and say, oh, okay, I understand the intuition behind that completely, and I totally get what this means. Now, if you read it out in words, the formula looks something like this. It's the terminal value times the discount rate minus the final year free cash flow divided by final year free cash flow plus the terminal value. I'm going to show you where this comes from, and I'll have to warn you in advance that yes, there will be some math involved, but you are watching Excel-based videos on YouTube, and I hope you are good at math and you like math if you're actually watching all this. So let's go through the full derivation right now for this and go through what it actually means. Remember that the formula for terminal value, if you're using the long-term growth rate, so if you're not using an EBITDA multiple, if you're using the company's long-term free cash flow growth rate, it's just equal to the final year of free cash flow times 1 plus that growth rate divided by the discount rate minus the growth rate. And we've been over the logic for that in some other tutorials and other series here, so I'm not going to go through it here again, but that's the starting point. Now, the challenge here is that we know what the terminal value is going to be. We know what our final year free cash flow is, we know what our discount rate is, and so we're going to have to solve this equation for the free cash flow growth rate by rearranging many of these terms. Now it's going to be somewhat challenging because when we do this, as you can see, one of these terms is in the numerator, one is in the denominator, and so I'll have to go through some algebraic manipulation to get them both on the correct side. So the first thing that we do here is get rid of the denominator, and so we multiply both sides by the discount rate minus the free cash flow growth rate. By doing that, we essentially take this term over to the left-hand side of the equation. Now it's just terminal value times the discount rate minus the free cash flow growth rate, and that of course is equal to our numerator that we had before, the final year free cash flow times 1 plus the growth rate. So we have that, but we still have growth rates that are on different sides of the equation here. So the next thing that you can do is separate out the terms like this. You can just multiply everything across and carry through that multiplication operator. When you do that, you get terminal value times the discount rate for the first term here. And then for the second term, you multiply the terminal value times the negative free cash flow growth rate. So you get minus terminal value times free cash flow growth rate for the second term in this equation. And then the right-hand side, you just have 1 plus the free cash flow growth rate So final year free cash flow times 1 is just final year free cash flow. And then final year free cash flow times the growth rate is just final year free cash flow times the growth rate. So this is what we have. We're getting a little bit closer because at least now we have those growth rate terms separated out a little bit. But of course, there is more to do here. So let's keep going. This is where we just left off in the last slide. Now the next thing to do here is that we want to move everything over to one side of the equation and make the other side equal to 0. So this whole first part, we're keeping this on the left-hand side of the equation. And then what we do is take everything on this side, final year free cash flow plus final year free cash flow times the growth rate, and then we just subtract it. We cancel it out of this side, subtract it, and move it over to the left-hand side. So minus final year free cash flow minus final year free cash flow times free cash flow growth rate equals 0. So we're getting closer because now at least we have that growth rate term on the same side of the equation, and now we can start to group together some of these terms to get the free cash flow growth rate all by itself on one side of the equation. So here's what we can do next. We can just put all the terms that involve free cash flow growth rate on the left-hand side of the equation as I've done here. So terminal value times free cash flow growth rate, this has a negative sign in front and we're therefore going to keep it on the side. And then the other term that involves it is minus final year free cash flow times the growth rate. We are going to keep this one on the left-hand side of the equation as well. And then those other two terms, terminal value times discount rate, we're going to move that over to the other side. So we'll put a negative sign in front. And then final year free cash flow, it has a negative sign in this former equation. And the new one, we have a plus sign because we've moved it to the other side over here. So we're making some progress, and you can start to see our strategy here that we're really trying to separate out that growth rate term on the left-hand side of the equation and put everything else on the right-hand side. So here's what we ended up with last time. Now let's continue with this and go through the next few steps to get to our final solution here. So now we get to the part where we can group the terms together. Since the left-hand side of the equation has this common term of the free cash flow growth rate, we can separate that out right here, and then we can multiply by the negative terminal value minus final year free cash flow. So we're really just grouping these and using free cash flow growth rate for our common term. And then on the other side, we haven't changed anything. It's still minus terminal value times the discount rate plus final year free cash flow. So we've grouped the left-hand side. And then what we can do is just multiply everything here by -1 to get rid of a lot of these stray negative signs. When we do that, when we multiply this equation by -1, we flip the signs of everything. So we get rid of these negative signs in the parentheses here, and these turn into positive signs. And then in the other equation, we make this first sign over here, we change it from negative into positive, and then the second sign is already positive and we make it negative by doing that. So we're getting very close to the end here, and you can probably already see what the next step is. We almost have the free cash flow growth rate separated out by itself on one side. So here's what we're left with, and then really the last step here is very simple. We just take the term we're multiplying by, the terminal value plus the final year free cash flow, and now we divide both sides by it. So now we put this in the denominator on the other side of the equation, and the result is this formula. Terminal value times discount rate minus the final year free cash flow, all divided by parentheses terminal value plus final year free cash flow, close parentheses. And that's how we got our formula. Now I don't know that there's a good intuition for this exactly. You might be able to come up with something if you stare at this long enough, but I'm not going to bother. I think this is one of those cases where there isn't necessarily great intuition for it, where you just have to understand where the formula comes from and the derivation here. Now, how do we actually use this in real life? Well, in this case, let's go back and take a look at our Excel file. So here, the conclusion is that our implied free cash flow growth rate, using that exact same formula I just showed you, is 0.5%. And when we calculate the terminal value using the long-term growth rate method instead, we're also using 0.5%. So it seems like both of our methods here line up, and they do exactly line up because I've picked the exact same numbers. But consider what would happen, for example, if we went back to our set of comparables and we said, okay, you know what? It seems like with some of these comparables, we have multiples that are much higher. We have multiples that are around 9x EBITDA. What would happen if we use 9x EBITDA right here? Well, then the implied terminal free cash flow growth rate would be 3%, which is probably too high for a company like this. If you think about it, the US GDP growth rate is around 3% for a mature, developed economy, if not lower than that. So a company that isn't really growing that much in an economy that isn't growing that much, it's probably going to have a long-term free cash flow growth rate that's much lower than this. And then if we came in and said something even more ridiculous, let's say we had a 20x EBITDA multiple. Well, now our free cash flow growth rate would be 5.7% in the long term, and this is just completely unreasonable for a mature company in a country like the US. Maybe if you're in China or Southeast Asia or another rapidly growing emerging market, this might be justifiable. Of course, the discount rate would also be much higher there. But in a mature, developed economy, you're not going to see free cash flows growing at that rate into infinity in the future. So that's a little bit about how you can do a check. And of course, you can do the same thing if you've calculated terminal value using the other method, the long-term growth rate method. And here it's very easy because you have terminal value, and then you can just divide this by the final year EBITDA, and this tells you your implied EBITDA multiple. So you can use both of these methods to check your work as you go along and to make sure, for example, that you haven't picked a multiple that's unreasonable, and to make sure that you haven't picked a long-term growth rate that is unreasonable. What are the conclusions that we can actually draw from all this analysis? And what's the point of all this in the end? We would point to a couple things. The first thing here is that this 5.9x multiple, and basing our range of values around roughly that value, we go from 4.5 to about 8.5. We don't think that's wrong necessarily because, again, the long-term growth rate implied by it is reasonable, and it is relatively in line with many of the multiples for the comparable companies. But there is a problem, which is that the terminal value, or the NPV of the terminal value, takes up around 74% of the total implied enterprise value from this analysis. Normally, you like to see this more like 50% or less, and you like to see more value coming from the actual free cash flows in the projection period. Based on this, we would say that we probably need to project out further. We probably need to go out more like 10 years or even 15 years maybe. And if you look at the free cash flow growth rates here, it definitely slows down, but we're still only down to around 9 or 10% by the end. Ideally, the final year free cash flow growth rate here should be somewhat closer to these figures, the growth rate that's implied by the multiple, or if we're using the growth rate method, the actual growth rate that we picked there. So that's conclusion number one. Conclusion number two, as I said, is that we should probably be picking a narrower range for this, because if you think about it, a multiple like 4.5x, this actually implies a negative long-term free cash flow growth rate for the company. We don't really think that's going to happen. Yes, it's mature, but it's not like it's a dying industry necessarily. Manufacturing is still growing, just not as quickly as other industries. So we might want to pick a narrower range. And on the upper end, we also don't really think that 8.5x is reasonable. Maybe we could go up to more like 7.5x and stop with that on the upper end. And then the final conclusion here is that it seems very likely that this company is overvalued at the moment. Its current share price is around $17.87. And if you look at this table, almost all these values are below that number. You have to go all the way over to the upper right-hand corner and go to very low discount rates and very high multiples to get share prices that are above that. And if you go down, you can see that theme pops up repeatedly, that we really do not get to that current share price unless we have very optimistic assumptions for the margins, for the final year multiples. And if you look at the revenue growth and operating margin table, we don't even get to that current share price at all. So those are some of the conclusions we can draw from this analysis. In short, the main takeaways from this lesson are that when you pick the terminal multiple in a DCF, yes, you might start with the set of comparables or precedent transactions, but you generally want to assume a discount over that. You want to make sure that multiples decline as companies get bigger. You want to always check the implied terminal growth rate and use the formula that we gave you for that down here. And then you also want to pick a good range of terminal values and a good range of long-term growth rates or terminal multiples when you're doing this. And then based on that, you can draw conclusions about the analysis and whether the company is overvalued, undervalued, or valued about appropriately.